This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is quality, a property of steam. We are given a liquid-vapor mixture at 110 C. We're asked to find the saturation pressure. We're asked to find the specific volume if the quality is 0. X is a symbol for quality, and quality is defined as the mass of vapor divided by the total mass. And C, we're asked to find the specific volume if the quality is 0.6. So here's our schematic. We've got a cylinder in which we have some vapor and some liquid in equilibrium, and it's trapped by a piston. When we're in the mixture region, we can use the lever rule to find properties. And when we're looking for properties, we need a table. And we're going to use the saturated water table, the temperature table. Now, we've got one. We'll look at that in a moment. But whenever you use a table, you need to tell your audience which table. So that's saturated water temperature table. And then from what source? If it's a book, you need to give the page number. If it's a web page, you need to give the web address. Whatever it is, you've got to be absolutely specific on where that table came from. And the reason is that everybody has an audience, and everybody has someone who reviews their work. For you, it might be a paper grader. For me, it's a fellow named Future Kevin, and he's pretty good at understanding what I've done. But I work with another guy named Former Kevin, and it really chaps me when he doesn't tell me exactly where a table came from. And his handwriting. All right, let's work on the problem. We're going to look at the temperature table here. Here is the saturated water table, and this is the temperature version, and that means that the first column is temperature in round numbers, and we can find in here the condition we need, which is 110 C. It's down here. And the value we're looking for is the saturation pressure, and it's listed right next to that. At the top of this table, every table has a trick. This table is, the trick is, the top part of the table is in kPa, and the bottom part of the table where we are is in MPa, or megapascal. So here's the value we want. We're going to pull that out and transfer that to the other table. So here's our condition. We're looking for the saturation pressure at 110 C, and the value we found on the table was 0.1433 megapascals. So in fact, that's our answer to part A, and we could write it this way: P saturation at this condition is at 110 C is 0.1433 megapascals. All right, and the answer is not complete until you say what the source was. All right, part B, what's the specific volume under the condition that x equals 0? And I've set up a little place here to write down our values. In the table we have a value for saturated liquid, V sub F, and a value for saturated vapor, V sub G. Let's go get those. So here the next section of the column has a specific volume, and we've got a value for saturated liquid and saturated vapor. Down here at the row that we need is the 110 C, and so those are the values we need. Let's see if I can expand that. Okay, and so the saturated liquid value is 0.001052, and the saturated vapor value is 1.2102. Let's transfer those to the other document. So here we need, I'm going to just write those down. The saturated liquid value was 0.001052, and the saturated vapor value was 1.2102. Now I didn't mention when I was looking at the other page that both of those are in meters cubed per kilogram. That's specific volume. Okay, how are we going to use that information? Well, at x equals 0, the definition of quality is the mass of vapor divided by the total mass. If x equals 0, that means that there's no vapor, therefore it's all liquid. And so the liquid value is the one we want. So the answer is V in this condition is the same as V sub F, which is 0.001052 meters cubed per kilogram. So that takes care of part B. And now let's look at part C, where we were asked to find the specific volume under the condition x equals 0.6. All right, this is where we're going to use the lever rule. Lever rule. And the lever rule for this case, for specific volume, says the specific volume at the situation we want is V sub F plus the quality times the difference between V sub G and V sub F. Now I want to explain a little bit about what the lever rule means. We're working on a TV space, and we're working in the mixture region. So here's the saturation line. And imagine that this is 110 C, and this point over here is V sub F. This point over here is V sub G, because this is the mixture region. And over on the one side is liquid over here, and over here is vapor. And mixture is in between. So the lever rule tells us about a distance. We're starting out at this point and we're coming across to some value V that we're looking for, and the distance is given by the quality. All right, we've got all the information we need to crunch this. We've got the VF and VG values that are transferred from the table, so let's compute this. V is going to be the liquid value, 0.001052, and the distance we are from that liquid value is 0.6, and the distance across the saturation, across the mixture region is this distance, V sub G, 1.2102, minus V sub F, 0.001052. So we crunch that, and that turns out to be 0.7264 meters cubed per kilogram. That's responsive. That's what we're asked to find. Quick check. Is this value in between the limits V sub F and V sub G? It's got to fall in the mixture region. And yes, it is. So, 0.72 is above 0.01, and below 1.2. So that's a check there. All right, let's recap. In this example, I'm struggling to scroll here. In this example, we're asked to study a mixture region problem at a given temperature, so therefore we're going to use a temperature table, and be sure to tell your audience which table. If we need to use the lever rule, it has the form of how far are we across the mixture region from here to here, and what distance are we? And when you're done, check that the value falls between. And if you remember that, all will be well.